Hello, I'm Masami Yamaguchi from Tohoku University. Today, I'd like to introduce Synbit, which is our new program synthesizer for bidirectional programs. Synbit synthesizes bidirectional programs using unidirectional sketches. Let us start with a background. Bidirectional transformation, which is also called BX, is a pair get and put. The pair is also called length. Here, we use the append function as a concrete example. If the input 1 and 2, 3 is given, append returns 1, 2, 3 as the output. The input is called source, and the output is called view in BX field. This forward transformation is called get. And then, consider the situation where this view 1, 2, 3 is updated into 1, 2, 3, 4. In this case, the source should be updated to 1 and 2, 3, 4 to make consistent with the view's update. This is backward transformation and called put. Put takes an original source and an updated view as input and return a new source. These bidirectional transformations are used for synchronization between multiple data in different formats. Of course, not all pairs of get and put are bidirectional transformations. There are laws to follow. The law is well-behavedness. Well-behavedness consists of two conditions: acceptability and consistency. Acceptability says no changes to the source if there is no change to the view. And consistency says all changes to the view must be captured in the updated source. We now understand what is bidirectional transformations, but as you can easily imagine, writing such kind of BX program is difficult. So, to reduce the difficulty of BX programming, special programming languages for bidirectional transformations have been studied. BX programming languages enable us to program both get and put together in one code. And in addition to that, programs written in BX languages are ensured well-behavedness. BX programming languages have been studied for a long time. This is an exact list of BX programming languages. However, even if we use the BX languages, BX programming is still difficult because programmers still have to think about the behavior of both directions. This is the intrinsic difficulty of BX programming. To address the difficulty of BX programming, our solution is synthesizing BX programs using unidirectional programs. From unidirectional program of get and IO examples, synthesize well-behaved BX programs automatically. Programmers are familiar with writing unidirectional programs, so we decided to use the unidirectional get as our input. It should help synthesis tasks in some way. And since this get is not always bijective, so there are many choices for its backward behavior. So, IO examples are needed to specify the backward behavior. And the output program must be well-behaved. To ensure the well-behavedness, we use a BX language as a synthesis target. So, next step is what language is suited for the target. We decided to use a BX language HOBiT as a target language because the structure of unidirectional program and its corresponding BX1 is similar. Let's see an example. The left code is unidirectional append, and right code is bidirectional append. First, look at the left one. Append function takes two lists, xs and ys, and considers two cases. If XS is empty list, then it returns YS. If the form of XS is acons X, then it returns acons append XYS. This is the usual append function. And next, please see the write code. The write code is bidirectional append written in HOBiT. It looks a little bit complex. The parts that is inside the blue box have a role in handling backward behaviors. And if hiding here, you can notice that the main structure of bidirectional append and unidirectional append is completely same. And thanks to the feature, the structure of unidirectional program and BX1 is similar. We can construct a sketch of BX programs using the structure of get. And here, sketch is an incomplete program whose main structure is given, but details are left as holes. For example, the upper right program is a sketch of BX program, because the main structure is given, but details are left as holes. And by using this technique that construct a sketch of BX program, we can focus on the parts that handles backward behaviors. This is our contributions. We propose Synbit, which synthesizes well-behaved BX program written in HOBiT from unidirectional get code and I/O examples. Synbit efficiently prunes the search space using the structure of get as a sketch of BX programs, and using domain-specific knowledge of BX programming languages. This is an overview of Synbit. The input is unidirectional get code and a few I/O examples. Synbit synthesizes bidirectional programs in 2 steps. The first step is sketch generation. As I mentioned, the sketch of BX program is obtained by using the unidirectional get code. And the next step is sketch completion. Synbit fills holes in the sketch and checks the behavior of candidate program against I/O examples. If the candidate program is consistent with I/O examples, Synbit returns the program as the desired bidirectional program. Let us see more details. The first step is sketch generation. In this step, the input is the given unidirectional get code and output is a sketch. In this step, unidirectional get is converted into a sketch by replacing language construct with corresponding BX ones. The next step is sketch completion. Sketch completion step consists of 2 sub-steps. The first sub-step is restricting the shape of holes. By using simple range analysis, we can roughly determine the shape of holes, so we can refine the holes to reduce the search space. Sketch completion step 2 is filling the holes. This can be done by component-based type-directed synthesis. The components that can be used here are auxiliary functions and constructors defined by users, and case construct. The final step is checking the candidate program against I/O examples. If the candidate program is consistent with I/O examples, Synbit returns the program as the desired program. And if not, loop back to the before steps non-deterministically. We have seen the basic algorithm of Synbit. Here, let us see the optimization techniques as we used. The most important optimization is modular completion process. Actually, we can fix the control flow of transformation before its execution by domain-specific knowledge of BX languages. This untightens the dependency between holes. And in addition to that, we used a technique to run incomplete programs. This can be done by lazy non-deterministic generation. Lazy non-deterministic generation is important even by itself because it enables us on-demand fashion to Explorer candidates. And now, the dependency between hosts are untightened, and we can run incomplete programs by using lazy non-deterministic generation. We can separate the whole completion process into some small completion processes. This is the modular completion process. Next, we come to benchmarks. We conducted many microbenchmarks. The environment is shown in the left and the results are shown in right. Look at the table. We succeeded to synthesize many examples. This includes reverse function, whose treatment is traditionally regarded as difficult in BX field, because its backward execution trace is hard to determine. And for lines and lookup, Synbit couldn't synthesize their BX programs. This is because their unidirectional ones and bidirectional ones have different structure, so they are out of scope of Synbit's approach. And we conducted comparative experiment with Smith, which is the state-of-the-art program synthesizer for usual unidirectional program. You can see the result in our paper. We conducted experiments for larger and more involved examples. About experiment transformation, this table is the excerpt of the result. Log-in is the number of lines of inputted unidirectional programs, and log-sim is the line numbers of synthesized BX programs. AST is the size of abstract syntax tree. As you can see, Synbit can synthesize big programs. And we also try to synthesize a bidirectional lexer and parser. This is the biggest program that is synthesized by Synbit among the experiment transformation experiment. From unidirectional program whose line number is 35, Synbit succeeded to synthesize 115 lines programs. This is so big. Let us discuss related work, especially BX programming synthesis. Optician is a state-of-the-art framework for synthesizing lenses. Synbit and Optician share their objective, that is, synthesizing bidirectional program. And both synthesizer ensures well-behavedness of their synthesized BX programs. Our Synbit is designed for its target language HOBiT and works well for the target, while Optician is designed for its target language Boomerang, and also works so well for its target. Boomerang is a BX language for expressing bidirectional string transformations. The only difference between Synbit and Optician is their target language, but this makes very big difference between Synbit's and Optician's approach. Optician takes regular expression types as an input to reduce the search space. Regular expression type is a special type that describes data formats on string. And since this regular expression type have cross connection to target languages, it is sweet to reduce the search space. This is very different approach from ours. The interesting point is that despite the very different approaches, both of them leverage the strengths of the underlying bidirectional languages for efficient synthesis. Finally, conclusion. We propose Synbit, which synthesizes well-behaved BX program written in HOBiT from unidirectional getcode and I/O examples. Synbit efficiently prunes the search space using the structure of get as a sketch of BX programs, and using domain-specific knowledge of BX programming languages. Thank you for listening.